You are a hologram, the physics secret of your brain that rewrites reality. You reach for a name you said 1,000 times, and it's gone. Blank screen. Then a warm smell, yeast, sugar, heat, slides in from a doorway, and the name returns with the room, the laugh, the shoes you wore. It's like the film burned a frame and the scene reassembled itself. Here's the claim. Your memories aren't filed in your brain. They're projected from patterns, which means identity, free will, and what happens when the projector glitches aren't abstract debates. They're personal. If your life is a hologram, where are you? To see why this isn't sci-fi, we need to go back to a lab accident. Revelation, roadmap, and commitment. We're going to move in a straight line. Physics to brain, to crisis, to meaning, because the order matters. First, the physics hint. Holograms store information in waves, not in little labeled boxes. Then the brain puzzle. Decades of lesion studies failed to uncover neat addresses for memories. Yet people still remember with fewer neurons, just fuzzier. After that, the radical experiments. Tiny cues, like a scent or a chord, pull back entire scenes. The quality drops with damage, but the whole shape persists. That's hologram behavior. Here comes the twist. What you see and remember isn't the system. It's the user interface your nervous system renders to stay alive. We'll track how neural populations encode information in frequency, timing, rhythm, phase, and use interference to bind features into a single experience. That's not poetry. That's measurable oscillations and pattern completion. We'll talk about the weird and we'll keep it grounded. Non-local encoding, distributed storage, interference patterns, yes. Telepathy and magical thinking, no. We'll show how resilience in olfaction, sleep replay, and cross-frequency coupling make recall possible from fragments. We'll look at how the projector fails. PTSD's overstamped patterns, déjà vu's false completes, hallucinations, self-amplifying loops, and what that says about precision and timing. The stakes are heavy. Treatments for dementia that target timing and cues, learning strategies that exploit frequency and sleep, legal ideas about identity when the projection can be remapped, and the darkest question, what happens if the projection ends? We'll rack up falsifiable predictions, flag speculation, and mark the line between metaphor and mechanism. So where did the idea come from? Not from mysticism, from a mid-20th century lab moment when a physicist knocked a plate, ruined the edges, and still saw the whole image, just blurrier. The physics seed, how holograms work and why physicists got obsessed. A hologram is a cheat that uses waves to hide a 3D scene inside a flat plate. You don't store the picture itself, you store the way light interferes with itself, the ripples. Shine a reference beam on an object. The light bouncing off it interferes with that beam, and where crest meet crest or cancel, a high-frequency pattern freezes onto the film. It looks like static, but it's not random, it's the object transformed into frequency space. Here's the property that hooked physicists, the hole in every part trick. Cut the plate in half, and each half still reconstructs the whole image at lower resolution when lit by the original reference beam. Keep cutting, and you never get just an ear or a shoe. You get the whole person, blurrier each time. In holography, information is spread out across the medium, not stamped into precise locations. That's non-local storage. Under the hood is Fourier math. Any shape can be expressed as a sum of waves at different frequencies and phases. The interference pattern on the plate is a Fourier domain encoding of the scene. The reconstruction is the inverse, transform, done by light itself when you shine the right beam. No CPU, no lookup table, physics does the math. If a smudge erases a region of the plate, you lose some frequencies, so fine detail and contrast suffer. But the global structure survives because other parts still carry overlapping information. Now for the coffee spit moment. A researcher cracks a holographic plate, curses, tapes a fragment to test the damage, and lights it. The whole object floats there, ghostly but intact. That is the moment your gut learns something your head hasn't caught up with. In wave-encoded systems, damage degrades fidelity, not categorical presence. That's a different failure mode than a hard drive, where a missing sector deletes a specific file. Physicists got obsessed because holography taught them two things. One, information can be represented in frequency rather than place. Two, interference makes storage and computation happen through superposition. Many components mingle in the same medium without overriding each other, as long as their frequencies and phases are handled correctly. You can even pack multiple holograms into one plate by changing the reference beam's angle. Tilt the beam back the right way, and you retrieve the one you want. That's multiplexing, a concept that jumps easily to signals, radios, and yes, neural rhythms. Stakes? If a biological system used anything like this, damage wouldn't delete grandma's cookie recipe and leave your piano lessons untouched. It would blur everything a little, then more, then a lot. Fragmentary cues could still unlock whole scenes, but with reduced clarity. Bits of the object would be recoverable from many places because the code wasn't about location, it was about frequency and phase. Engineers also loved how holograms naturally filter noise. Because reconstruction requires the right reference beam, random light doesn't easily read the image. And because detail lives in high frequencies, a partial loss mostly hits fine structure first. The system degrades gracefully. That word, gracefully, is code for robust in the face of damage, a trait evolution tends to favor. Meanwhile, the math behind holography, Fourier transforms, and Gabor functions started showing up in sensory science in the late 1940s and 1950s. Edge detectors envision receptive fields that look like little rippled patches, all suspiciously similar to the kernels used to analyze images in frequency space. When you see a neuron respond to specific orientations and spatial frequencies, you're watching a biological tissue act like a tiny filter, passing some waves and ignoring others. But hold the brakes. A hologram is made of light in a carefully controlled setup. The brain is warm, wet biology. The claim isn't that your cortex is literally a laser plate. The claim is that wave-based encoding, distributing information over frequency and phase, creates properties we can test, whole in every part. Like resilience, pattern completion from partial cues, graceful degradation of detail, and multiplexing by timing. Think about multiplexing for a second. In optics, you store multiple images in one plate by altering the reference beam's angle. In signal processing, you stack channels in different frequency bands. In the brain, you see multiple rhythms, slow theta, fast gamma, coupling, so features can travel together without crashing into each other. If those rhythms act as the angles of a biological reference beam, you can layer content in the same tissue and call it later by timing. Here's a micro story to land it. A graduate student drops a coffee mug onto the table, holding a hologram test. Crack, swear, paper towels, the usual. When the room calms down, they put a broken shard in the mount, switch on the beam, and watch a tiny, hazy teapot hover in the air. Still three-dimensional, still there. That image sticks because it rewires your expectation. A broken thing that still contains the whole. One more detail that matters. Fourier space doesn't care about where a feature is. It cares about which frequencies compose it. Shift the scene in space, and its Fourier magnitude barely changes. You alter phase instead. That separation, content in magnitudes, placement in phase, is a power move. It means the system can represent what and where differently. Later, when we look at how brains bind features into a unified percept, phase will be doing quiet, essential work. So physicists left the optics lab with a toolbox: interference, superposition, Fourier representations, and multiplexing. The question drifted into neuroscience, like a seed with burrs. If a brain harnessed wave codes, would its memories behave more like files or like holograms? Meanwhile, in clinics and animal labs, something stubborn refused to fit the file cabinet model. While that was happening in physics, a different kind of accident kept happening in neuroscience, especially through the 1940s, 1960s. Remove tissue here, and nothing specific vanishes. Everything just gets a little worse. The neuroscience puzzle, Lashley's Engram hunt, and the missing address. To understand why brains don't act like hard drives, we need to sit with a man who tried to find the file cabinet and came up empty. Carl Lashley spent decades cutting, scorching, and carefully removing bits of rat cortex to find the engram, the physical address of a learned memory. The setup was simple and brutal. Train a rat to run a maze, let it prove the skill is solid, then lesion a region and test again. If memory is a thing with the home, damage the home and the behavior should collapse in a specific way. But the collapse never behaved. Rats with damage to one area could still run the maze, slower, sloppier, but not erased. Move the lesion elsewhere, same story. You could carve lots of cortex and the rats got worse in proportion to how much tissue they lost, not where you took it from. Lashley called it mass action, the idea that the cortex works as a whole to support complex behaviors. He paired it with equipotentiality. Remaining tissue can take over functions, at least partially. What he didn't find was a mailbox labeled maze memory, back left drawer. Here's the human angle. Stroke. Survivors can lose swaths of cortex and end up with blurred abilities, not a single cleanly deleted memory. A face that used to snap into recognition now stalls. Feels familiar but won't resolve. A word sits just out of reach, not wiped, just misindexed. It's the same signature Lashley saw in animals. Performance degrades with volume of loss, not with precise coordinates. That's not how you'd expect it to look if memory lived in discrete parcels. Lashley's failure wasn't a dead end, it was a signal. If engrams weren't sitting in one spot, maybe they were patterns. Distributed, overlapping, and resilient. He lacked the tools to see patterns. The mid-century cortex was a black box. Action potentials along axons were easy to record. The subtle ballet in dendritic webs was not. So Lashley's conclusion was cautious and maddening. "I sometimes feel," he wrote, "that the necessary conclusion is that learning is just not possible." He didn't mean it literally. He meant the model on offer, engrams as local stamps, didn't fit the data. Meanwhile, micro-stories from clinics kept whispering the same thing. A patient loses part of the temporal lobe and struggles with names, yet give them a smell from their childhood kitchen and an entire Sunday afternoon returns. The checkered tablecloth, the scrape of a chair, the rhythm of a parent's footsteps. Clarity isn't perfect, edges are smudged, but the scene is whole. Another patient's stroke leaves their speech halting, yet a familiar song lets them sing full lines. Function routes around damage. The pattern seems intact, but harder to access. This was the moment everything changed. Not because a single experiment answered the engram question, but because the failure to find addresses forced a pivot in language. Instead of "where is the memory?" the better question became, what population dynamics sustain this memory? If performance loss scales with tissue loss, we're looking at codes smeared across networks. If partial cues can trigger full recall, we're looking at pattern completion. There was one problem: without a map of microstructure. Pattern sounded like hand-waving. Lashley's critics wanted specifics. Which neurons, which layers, which signals? The answer would have to wait for new methods, multi-unit recordings, better lesion controls, and computational models that could test how distributed codes behave under damage. But the broad shape of Lashley's law kept showing up. Across tasks, the severity of impairment tracked the amount of cortex removed. The missing address wasn't hiding, it was the wrong metaphor. From the rat room, we can jump to a kitchen table to see how this felt. Get this, researchers would lesion one hemisphere and watch rats struggle a bit, then train them again. With time, performance improved. Add a second lesion, and the animals dipped, then clawed back again. The behavior was plastic. Memory as a static trace didn't explain the rebound. Memory as a dynamic pattern, constantly re-engraved by use, did. What nobody knew at the time was that the cortex's fine-fibered dendritic webs were exquisitely tuned to rhythms, the very stuff of waves. Lashley couldn't measure those rhythms, but he could see their consequences: graceful degradation, redundancy, and the absence of a single point of failure. His maze data were the behavioral shadow of a system organizing information in a distributed code. While that was happening in animal labs, neurosurgeons started to map human functions with electrical stimulation during awake surgery. Touch one spot, a patient tasted metal. Touch another, a memory fragment fluttered up, partial, noisy, rarely a full delete or full play. The brain felt less like a library of books and more like a chorus that could hum the whole tune with fewer singers, just not as sharply. To understand why that chorus could hold a song without a single soloist, we need a tool Lashley didn't have, a way to look at signals in frequency and phase. That would arrive with Carl Pribram and the math of Fourier transforms, an invitation to see the cortex not as storage slots, but as a medium where interference patterns carry content. Frequency brains, Pribram, Fourier transforms, and the cortex as a hologram. Carl Pribram walked into this puzzle from surgery suites and psychology labs, not from an optics bench. He kept seeing the same mismatch. Action potentials along axons explained fast messages, but perception had textures that felt wave-like. Context, blending, the way a whole scene snaps in from a hint. He turned to Dennis Gabor's mid-20th century mathematics and asked a blunt question. What if the cortex represents information in frequency and phase, then reconstructs experience by interference? To see why that isn't airy, look at the cortex's microarchitecture. Under the microscope, you don't just find long cables firing all or none spikes. you find fine, branchy dendritic webs that some inputs and gradients, and crucially, resonate. Those dendrites, layered through cortex, form receptive fields that behave like filters. They respond best to certain orientations and spatial frequencies in vision, certain modulations in sound, particular temporal rhythms in touch. In other words, they look like biological Gabor filters, little rippled patches that carve the world into frequency components. Here's where Fourier transforms enter the story. Any image can be decomposed into sinusoidal gratings at different spatial frequencies and orientations. In primary visual cortex, neurons are tuned to exactly those gratings. Present a bar tilted 15 degrees and one set fires. Shift the bar and a different pattern lights. Shift the bar's position without changing its frequency content, and the overall strength of responses hardly changes. What changes is timing and phase relationships. That division, content carried in frequency selectivity, placement adjusted by phase, tracks the hologram math Pribram leaned on. But he didn't just make a metaphor. He pointed to mechanisms. Population activity across columns and layers generates oscillations. When you measure local field potentials, you see rhythms spanning slow theta to fast gamma. These rhythms aren't background noise. They gate when neurons can influence each other. Two assemblies firing in sync at a particular phase couple more strongly than ones out of phase. That's interference in biological tissue, superposition, and timing, determining what pattern wins. The stakes are immediate for perception. Think about edges. Your retina sends a messy, contrast-limited signal. Cortex sharpens it by aligning responses to specific spatial frequencies, then combining them. If phases across those frequency channels lock in a consistent relationship, you experience a crisp contour and the surface that belongs to it. If the phases drift, the contour loses snap. This is why a visual illusion can push your system to interpret the same intensities as different shades. Your brain is reconstructing from frequency cues and priors, not passively reading pixels. Now remember Lashley's puzzle. Remove tissue and behavior degrades with amount, not place. Frequency domain codes explain that signature. If the what of a scene lives across populations tuned to many frequencies, then slicing out any subset removes some bands. Fine detail fades first. The gist persists. You don't need a single neuron labeled grandmother to fail spectacularly. You need a distributed loss that erodes the spectrum that defines her face, her voice timbre, the cadence of her walk. Pushback came fast. Isn't this just a fancy analogy? Pribram answered by pointing at concrete correspondences. The mathematics used to describe ideal receptive fields. Gabor wavelets, Wigner distributions are also used in optics to analyze holograms and diffraction. Early studies mapped cortical responses to two-dimensional Fourier components, not just point-by-point features. And later, multi-electrode recordings showed something deeper. The timing of spikes relative to ongoing rhythms can carry as much information as the spikes themselves. Phase of firing codes allow a neuron to say different things without changing its rate, like writing multiple messages on one carrier wave. Here's where the cortex as hologram claim earns its nuance. No, the brain isn't storing optical interference patterns. Yes, it's building interference patterns in electric fields and synaptic currents. These fields bias which inputs some constructively and which cancel. A memory in this view isn't a fixed trace, it's a stable attractor. A pattern of synchronized activity that can be re-entered when the right partial cue nudges the system. You shine the reference beam of ongoing rhythms through a fragment, and the full pattern settles in. Consider multiplexing. In optics, you angle the reference beam differently to pack multiple holograms into one plate. In cortex, you can couple different content to different phases or frequencies. Theta cycles in the hippocampus can bracket sequences. Nested gamma bursts can bind features within each moment. Adjust the phase, and you retrieve a different chunk of the sequence. That's not philosophy, it's been measured as theta. Gamma coupling during memory tasks and replay during sleep. The human feel of this shows up in micro-stories. Someone hears 3 piano notes, do-re-mi, and suddenly the kitchen from 1998 unfolds. The notes aren't the picture. They're a key that lines up phases across frequencies in auditory and association cortex. Once alignment crosses a threshold, the larger pattern completes. If the underlying circuits have lost high-frequency precision, aging, trauma, disease, the same key yields a hazier scene. That's pattern completion and graceful degradation in lived time. Pribram didn't ignore alternatives. He compared his holonomic account with models focused on spike timing propagation along axons. He argued they're complementary. Axons carry packets, dendritic and field. Dynamics shape the carrier's meaning by aligning or misaligning phases. He also drew a boundary around quantum talk. Yes, the math overlaps with quantum formalisms, but you don't need long-lived quantum coherence in neurons to get interference in classical fields. Warm, wet biology can still run frequency codes. So we land here. The cortex behaves like a medium that encodes and reconstructs information through distributed frequency tuning and phase-locked interference. That yields the signatures we can test: robustness to localized damage, pattern completion from fragments, and multiplex content on shared tissue. A metaphor becomes a model when it predicts failures. To see those predictions play out, we need to turn to the strangest evidence of all: memories that survive amputation of their supposed homes and return on the back of a smell, a rhythm, or the pulse of a sleeping brain. The radical evidence: distributed memory and neural waves. Stakes first. If memories live as distributed patterns, then a sliver of the right cue should be able to light up the whole pattern. And when tissue is lost, recall shouldn't vanish by category. It should smear. Less detail, more noise, same gist. That's exactly what clinicians and labs keep seeing. Action. Start with pattern completion. You've lived it. A single chord, a whiff of cinnamon, the crunch of a certain gravel, and an entire scene unfolds. Faces, angles of light, a sentence you didn't know you stored. In controlled studies, tiny cues reliably trigger structured recall. In vision, presenting partial contours can provoke recognition of the full object before the missing lines arrive. In audition, leading intervals seed the brain to hear the song's continuation. In olfaction, the effect is louder. A simple ester can pull associated places and episodes on a short latency, and those associations survive damage that would cripple other modalities. Impact. Pattern completion isn't a party trick, it's a fingerprint. Hologram-like codes reconstruct from fragments. The brain's version runs on timing. When a cue aligns phases across frequency-tuned assemblies, constructive interference ramps up, and the large-scale attractor, the memory, snaps in. Meanwhile, something else is happening in the hippocampus and cortex. They split the labor. The hippocampus is a brutal librarian. It separates similar experiences during encoding, so today's coffee shop doesn't overwrite last week's rim. Cortex is the archivist. It generalizes and fills in. Recordings in animals show pattern separation, neurons and dentate gyrus that diverge activity for near-identical inputs. Later, CA3 recurrent connections and cortical loops support pattern completion. We're entering a stored trajectory from a partial start. Human imaging echoes this. Lure items that are nearly identical to studied items drive different hippocampal signatures at encoding, but later retrieval lights up familiar patterns from minimal cues. Microstory. A patient lives with most of one temporal lobe gone after surgery for seizures. Names are hard. Daily details slip. But one afternoon, walking past a bakery, the smell of warm bread rises, and a childhood song rides in with it. Melody, the tinny radio, a cousin's red jacket, the exact chipped counter. The patient can't place the album, but they can hum the verse. The content is everywhere. The fidelity is down. That is the blur not delete signature in human time. Stakes. If damage reduces resolution, therapy should aim to boost precision, phase alignment, timing windows, targeted cues, not just brute repetition. And diagnostics should map how blur scales with lesion size, not chase a single missing file. This matches classic findings from the 1950s, 1960s lesion literature and modern imaging. Action. Distributed degradation shows up across species and methods. In rodent maze learning, lesion volume predicts performance drop better than location, unless you cut specialized bottlenecks. In humans, diffuse neurodegeneration, early Alzheimer's, vascular burden, shaves off detail before it deletes categories. People remember the event, but confound specifics. The restaurant, yes. The waiter's face, no. The table's position, off by a few feet. In language, anomia feels like phase drift. Phonemes are close, syllable swap. A neighbor word lands. None of this looks like a clean file gone missing. It looks like high frequencies lost first, then mid, then low. Impact. This gradient of loss maps neatly onto frequency domain coding. High frequency components encode edges, fine distinctions, timing precision. Knock them out with aging myelin loss, reduced inhibitory balance, or tissue death, and the system defaults to gist. That's not apologia, it's a measurable prediction. Interventions that restore high-frequency coherence should sharpen recall even when neurons are gone. Action. Now to oscillations. Gamma, around 30 to 100 Hz, often tags local feature binding, color with edge, pitch with onset. Theta, 4 to 8 Hz in humans, paces sequences and sets windows for when groups can talk. In episodic tasks, the two couple. Gamma bursts nest inside theta cycles. The timing of those bursts relative to theta phase carries information about order. In hippocampus, this phase code appears during learning and replays during rest and sleep. Wake an animal after learning a track and you'll see compressed sequences ripple off in the same order, often aligned to sharp wave ripples. Fast transients coordinating long-range communication. Disrupt those ripples and memory consolidation suffers. Stimulate on phase and recall can improve in controlled settings. Impact. That's not metaphor, that's a control knob. Stimulation of hippocampal theta during encoding enhances later recognition. Aligning stimulation to individual theta phase beats out random pulses. During sleep, coupling slow oscillations with spindles and ripples by auditory clicks timed to slow wave upstates boosts targeted memories without boosting others. That's multiplexing in action. Action. Phase coding extends beyond the hippocampus. In sensory cortex, the phase of firing relative to local field rhythms can carry stimulus identity independent of rate. Two neurons with identical spike counts can encode different content by shifting when they fire within a cycle. Across distributed areas, cross-frequency coupling allows channels to coexist. Slower rhythms set the context window. Faster ones deliver content. Attention sharpens phase locking. Distraction smears it. When attention falters, gamma coherence between distant sites drops and feature binding errors rise. When attention is trained, coherence increases and the system resists noise. Microstory. A guitarist loses motor control in the dominant hand after an accident. The songs are gone. Months later, they start training the other hand. At first, it's clumsy. Then something strange happens. Progress accelerates in leaps. Old songs reappear faster than new ones are learned. The hardware changed. The song, the pattern, survived. The brain rerouted execution to new effectors while retrieving the same distributed memory with lower precision and rebuilding the high-frequency detail by practice, i.e., by sharpening timing. Stakes. Rehabilitation built on frequency and phase can speed remapping. Metronomes, rhythmic entrainment, breath pacing, and synchronized multimodal cues can act like reference beams, aligning distributed assemblies so the reconstructive wavefront has a cleaner path. Action. The connectome adds redundancy. Multiple pathways can produce the same output. Degeneracy, in the good sense. Knock out a node and traffic routes around it with extra latency. Learning then prunes and strengthens the new path, restoring speed and contrast. After stroke, speech networks recruit paralasional tissue and contralateral homologs. Training that emphasizes rhythm and prosody, temporal structure, often outperforms semantic drills early on. Why? Because timing reestablishes the interference pattern before content refines it. Impact. This is the opposite of a library. It's more like a stadium chant. Lose a section and the chant continues, softer and less crisp until the crowd adjusts. Your cortex is that crowd, pulsing in time. Action. Sleep shows the system stitching holograms at night. During non-REM, slow oscillations group spindles. Spikes replay compressed sequences. Hippocampus talks to cortex in bursts, cueing a memory with a related sound during the right slow wave phase. Selectively strengthens that memory the next day. Miss the phase, and the effect largely disappears. The cue isn't the file. It's the handle that aligns phases for replay. In motor tasks, targeted memory reactivation during slow wave sleep can improve precision of specific sequences. In language, cueing vocabulary during slow wave boosts, recall without contaminating uncued words. Layered holograms accessed by the right reference timing. Impact. This is the multiplexing prediction again. If multiple memories coexist in overlapping tissue, you need a way to call one without calling the others. Phase and frequency serve as addresses. Action. Critics push. Couldn't all this be explained by plain synaptic plasticity without wave talk? Sure, synapses change, but plasticity needs a teacher signal, and waves provide it. Temporal windows where spikes change weights more or less. Spike timing-dependent plasticity is phase-sensitive. Without rhythm scaffolding, which spikes count as together, you'd learn slowly and sloppily. With rhythms, you learn compositional structure efficiently, like separating instruments on different tracks and recombining them later. Microstory. A lab rigs up a closed-loop system. It watches a subject's hippocampal theta, then delivers a tiny pulse only at a chosen phase, while the person encodes pairs of pictures and locations. Later, those pairs are recalled more accurately than pairs encoded with pulses at random phases. Same brain, same pulse strength, different timing. The projector's interference improved reconstruction. Stakes. If timing is the handle, then diseases that flatten or desynchronize rhythms should hurt memory even when neurons survive. That's what we see. In mild cognitive impairment, gamma power and cross-frequency coupling often fall. In schizophrenia, gamma synchrony and long-range coherence are disrupted, and feature binding suffers. In depression, sleep spindles can weaken, consolidation dips. Interventions that restore rhythm, non-invasive stimulation, auditory entrainment, and pharmacology that balances inhibition show early promise in sharpening recall and perception. Action. There's one. More clue. Graceful recovery after partial damage. After unilateral hippocampal resection, patients often show initial deficits in forming new memories of specific types. Over months, many improve. Cortex picks up weight. Contralateral structures adapt. Training that leverages multiple cues, visual, auditory, proprioceptive, accelerates this. Each cue carries overlapping frequency content. Together, they raise signal to noise, letting the system converge on the intended attractor despite fewer high-frequency components. Impact. The practical read is blunt. Don't just repeat content. Engineer cues that control timing, beats, breaths, saccades, light flicker, and pair them with sleep. Use spacing that exploits natural rhythms of consolidation. Design rehab that treats memory as a pattern to be aligned, not a box to be found. Stakes. Because this isn't philosophy class, this is identity. When your projector glitches, your world blurs. If the evidence is right, you can tune the projector. And if the whole is in every part, then pieces of you remain accessible even when some parts are gone. Information physics, entropy, predictive coding, and the UI of reality. While those waves are doing the binding, another engine is running underneath. Compression. The brain isn't trying to store reality, it's trying to predict it with the fewest bits that still keep you alive. That's predictive processing. At every moment, higher regions send down guesses about what the next sensory input should look like. Lower regions send back only the differences. Errors. Minimize the error, and you've compressed the world. This framing aligns with predictive coding and active inference models developed from the late 1990s through the 2000s. Think of it as an information budget. Entropy is the cost. A disordered scene takes more bits to describe. Your brain pushes against that cost by learning regularities, edges, rhythms, voices, your front door squeak. The more you've learned, the fewer surprises you pay for. That's why expertise feels quiet. A chess master's board is low entropy because their model compresses it. A novice's board is noise. Here's where frequency earns its keep again. Efficient codes tend to live in frequency space because natural scenes have regular spectra. Lots of low-frequency gists, fewer high-frequency details. If you move information into a basis where most energy sits in a few coefficients, you save bandwidth. That's what JPEG does with cosine transforms. It throws away barely visible high frequencies and keeps the big structure. The cortex seems to do its own version, represent predictable backgrounds with slow rhythms, and deploy fast components only when needed. When energy costs spike, fatigue, illness, the system defaults to coarse predictions. You see the thing you expect and miss the small mismatch. Now layer in the UI idea. A desktop icon doesn't show you the machine code inside a file. It shows you a useful sketch. Perception works like that. Your constructs, color patches, edges, objects, faces are icons for survival-relevant regularities, not faithful reconstructions of physics. They're cheap to update, quick to act on, and always slightly wrong. That's a feature. A perfect rendering would be slow and expensive. Evolution bet on speed. If that sounds abstract, watch your brain handle lighting. In the checker shadow illusion, two squares with identical physical luminance look different because your model predicts a shadow and corrects for it. You see the corrected surface, not the raw measurement. The brain is subtracting expected illumination frequencies, leaving you with a stable surface icon. The error signal, What didn't match drives a tiny update. You feel none of the math, you feel a world. Here's the trick that ties it back to holograms. Predictive coding needs a reference to compare against what you expect. Then it needs to interfere that with what arrives to reveal the difference. That's literally interference. The expected and actual signals superpose. Mismatches stand out as beats and phase slips. Circuits tune to those slips pass the errors up the hierarchy. Meanwhile, the matched portions cancel, saving bandwidth. Constructive for surprise, destructive for agreement. Entropy sits in the middle as a knob. When the world is volatile, new city, new job, your model raises its precision on error signals and lowers its trust in priors. You learn fast, your rhythms shift to favor exploration. Broader gamma bursts, looser coupling. When the world is stable, your kitchen, you crank up the prior's weight, suppress error noise, and glide. Too much prior weight, and you hallucinate the expected. Too much error, and you drown in noise. The sweet spot is adaptive. Precision weights change by context, neuromodulators tune the gain, and rhythms set the timing windows to catch just the right differences. Get this. Pain offers a stark example. Chronic pain often reflects a model that predicts threat from benign inputs. The system assigns high precision to priors like "this movement hurts," so ambiguous signals get interpreted as danger. Therapy that changes prediction, graded exposure, attention training, literally shifts precision settings. Entrainment, breath pacing, and slow interoceptive rhythms can downweight error noise so new priors can take hold. You're editing the interface. Why call perception a UI? Because the same scene can render differently depending on your task. If you're catching a ball, you see trajectories in time to contact. If you're painting, you see gradients and edges. The underlying photons are the same. The chosen code, what frequencies matter, which errors get promoted, changes. Task demands retune coupling between areas. Attention changes phase relationships. The interface reconfigures on the fly. This is also why illusions teach us more than veridical scenes. They expose the priors. Hollow masks look convex because face priors are heavy. Shepherd tones rise forever because your auditory model collapses pitch into a loop. The checkerboard fools you because your luminance model assumes shadows. In each case, the error signal is weak, the prior is strong, and your UI prefers the cheap explanation. Notice the survival angle. An organism that compresses effectively can act sooner and learn faster. It can assign precious spikes to the unexpected and ignore the rest. Sleep then sweeps the day's error signals into long-term changes, consolidating useful priors. Dreams might be the offline UI stress test, running the model without sensory constraints, probing edges, stitching stories to keep the generative code coherent. One caution before we drift into quantum land. None of this requires spooky physics. The holographic in our story is signal processing, distributed frequency codes, interference, and prediction error. It's non-local within tissue, not non-local across space. Decoherence is brutal in brains. We're not positing long-lived quantum states holding your childhood. We're saying your cortex behaves like an efficient codec with a great UI, built from rhythms and synapses. So when your projector glitches, trauma, sleep loss, disease, watch what fails. Precision weighting skews, rhythms desynchronize, and priors misapply. The UI flickers. Fix the timing, tune precision, feed better cues, and the picture steadies. That's practical hope, not mysticism. You can edit your interface by training the code that predicts it. Glitches in the hologram, trauma, hallucinations, and reality drift. When timing is the handle and priors are the code, you can guess what failure looks like. Gain turned up too high, phases slipping, and the UI filling in what isn't there. Trauma shows the loud version. After a blast or assault, the memory doesn't just strengthen, it saturates. The system stamps a high precision pattern. Sound, smell, posture, light angle. So hard that any overlap in frequency space triggers completion. A car backfires and the entire scene reconstructs. Body locks, breath spikes, the old room overlays the current street. The projector isn't broken, it's overconfident. Stakes here are human. A veteran sits in a diner. The hiss of the kitchen matches the spectral band from a generator overseas. That slice is enough. Interference pulls the full pattern. the diner dims into a checkpoint. The brain's job is to pick survival-relevant icons quickly. After trauma, the weighting tilts toward threat, and the overlap needed to complete the pattern shrinks. This is PTSD as overstamped interference. High gain, rapid lock, little tolerance for mismatch. Actionably, therapy targets precision and timing. Exposure with safety cues teaches the system to reweight error. This hiss isn't that generator. Breath pacing and slow exhale recruit vagal rhythms that widen timing windows, so cues arrive in a calmer phase state. MDR time saccades into a bilateral rhythm while recalling fragments. Critics debate mechanisms, but the practice manipulates timing, arousal, and cue structure, exactly the levers a frequency code would respond to. Over sessions, the intrusive pattern loses high-frequency snap. The same cue no longer detonates the full scene. Hallucinations sit on the other side. Priors outrun data. In psychosis, the projector fills from expectation with little constraint. Auditory cortex runs hot. Speech, like rhythms in the brain's own activity, get misattributed as external voices. If gamma-theta coupling goes off and top-down precision gets oversized, the system promotes internally generated patterns as if they were error signals. You hear the model. Antipsychotics dampen dopaminergic gain on precision. Cognitive therapy trains reality testing. Slow down, seek mismatches, retune weighting. Get this, everyone hallucinates a bit. Close your eyes in a quiet room. Watch swirling phosphenes. That's cortex idling, generating patterns with no input. The difference in illness is calibration, without tight phase. Coordination between areas, the UI can't pin icons to stable causes. The world breathes unnaturally, meaning slide. Deja vu is a tiny, mostly harmless glitch. Faulty pattern completion from frequency similarity. A current scene partially overlaps a stored pattern, temporal rhythm, spatial frequency layout, and the hippocampus biases toward already seen. The tag for familiarity fires before the tag for source. You feel the click of completion without a file to attach. It passes because the system quickly discovers the mismatch and downweights the prior. Dreams are sanctioned glitches. Offline reconstruction runs without anchors. During REM and NREM transitions, the brain rehearses, stitches, and stress tests the generative model. Wild plots aren't mistakes, they're probes. The model blends frequency components from distant memories, trying new alignments, meaning get stitched from noise. Wake during the wrong phase and you carry a residue. Sleep inertia, a temporary desynchrony where priors feel sticky and inputs lag. Migraine aura offers a window into how sensitive timing is. A wave of cortical spreading depression sweeps across visual areas, temporarily altering excitability. Edges crawl, zigzags appear, blind regions open and close. It isn't in your eye. It's the projector's spatial frequencies falling out of register as excitation and inhibition slide. The UI struggles, the world looks unstable. Psychedelics push timing and priors deliberately. Lowered integrity in high-order networks, loosened precision on predictions, and increased entropy in spontaneous activity let bottom-up data flood in and priors soften. That's why colors bloom and boundaries melt. Therapeutically, the window can allow stuck patterns, like trauma stamps, to be rewritten when paired with safe context, music as a pacing scaffold, and trained guides. The risk is drift. Without structure, the system can encode noisy associations. Integration practices, sleep hygiene, breath, movement, schedule, help relock phases. Clinical evidence is emerging, but still developing. Anxiety is a chronic version of misweighting. The system assigns high precision to uncertain threats. Harmless cues complete into danger patterns. Attention narrows, gamma locks onto the wrong features, and you miss broader context. Breathwork widens interoceptive windows. Aerobic movement resets neuromodulators. Rhythmic practices like coherent breathing or synchronized steps act as metronomes for the projector. Over weeks, the UI stops painting hazard icons on every texture. Microstory. A barista hears the whir of a grinder and feels a surge of dread. Months earlier, that exact spectral whir overlapped a traumatic scene. In therapy, they pair the sound with new anchors, a counting rhythm, warm light, a friend's voice. At first, the old scene still tries to load. With repetition, the timing and context shift. The whir stays a whir, the projector learns a new completion. Alien abduction experiences during sleep paralysis. The model wakes before motor systems and proprioception do. With no movement feedback and a heavy prior for presence in the dark, the system completes a presence icon from interoceptive noise. Education alone, your projector is mistimed. Plus, sleep positioning, regular schedules, and phase reset strategies can reduce episodes. The dark edge is depersonalization and derealization. The UI's contrast drops. People report feeling like cardboard as if behind glass. That maps to hypoconnectivity between interoceptive areas and narrative networks. Low precision on body signals. Over-reliance on abstract priors. Treatment raises signal from the body. Temperature shifts, breath holds, cold exposure, paced movement, while reducing ruminations over coupling. Reality regains weight as timing between systems tightens. So glitches aren't random weirdness. They're lawful miscalibrations of gain, timing, and prior weight, which means they're trainable. Phase can be reset, precision can be tuned, cues can be tamed or retagged. And the same tools that reconstruct a memory from a fragment can help you unhook a fragment from a memory. Evidence you can't ignore, experiments that would break the model. If the brain runs on distributed frequency codes and interference, it should pass hard tests and fail in specific ways if we're wrong. So let's lay out experiments with clear predictions and the criteria that would sync this whole story. Start with lesion size versus blur. Prediction: as cortical tissue is lost, recall should degrade along a lawful curve. Fine detail first, gist last, largely independent of lesion location except at bottlenecks. You test this by mapping individuals' pre-injury sensory and memory resolution, then following them after focal strokes or resections. Use tasks that separate gist from detail. Face identity versus micro-expressions, scene category versus object count, word meaning versus syllabic structure. Quantify precision with psychophysics and neurospectral measures. If location, not volume, dominates degradation across diverse functions, clean deletions of single memories with small arbitrary lesions, our distributed claim takes a hit. Frequency training. Prediction: interventions that restore high-frequency coherence and cross-frequency coupling should sharpen recall specificity, even when neurons are gone. You'd run randomized trials with individualized neurofeedback targeting gamma power nested in theta during encoding, plus paced metronomes or visual flicker at safe rates. Pair that with spaced learning and sleep. Outcomes: tighter phase, locking across regions during tasks, and behavioral gains in lure discrimination, temporal order memory, and source recall. If we boost gamma/theta coupling and nothing about precision or binding budges, that weakens the interference account. Sleep manipulation. Prediction: timing matters more than total stimulation. Use closed-loop auditory clicks or gentle current time to a person's slow-wave upstates, and pair cues with just learned material. We expect targeted memory reactivation to improve only the cued items, with increased spindle, ripple coupling, and hippocampal cortical replay signatures. Miss the phase, lose the effect. If phase-locked cueing doesn't produce selective gains over sham or mistimed clicks, or if sleep signatures don't track behavioral improvements, the phase as address idea suffers. Closed-loop hippocampal stimulation. Prediction deliver pulses only at a specific theta phase during encoding, and later recall of associated pairs will rise relative to random phase or out-of-phase stimulation. This demands intracranial recordings in epilepsy patients already implanted for clinical reasons. Look for phase-specific enhancement in subsequent memory effects and cleaner reactivation at retrieval. If timing shows no advantage over power-matched random pulses, that dent hurts. Cross-modal cue multiplexing. Prediction: multiple overlapping memories stored in shared tissue can be selectively accessed by changing timing parameters of the cue. Design a task where two stories share actors and places but differ in order and soundtrack rhythm. Train each story under a distinct theta pacing and ambient beat. Later, cue with the same image while modulating the beat to match one story's training rhythm. Expect selective retrieval of the aligned story with distinct phase patterns across networks. If timing fails to disambiguate overlapping content, we lose a core multiplexing claim. Attention as a phase tuner. Prediction: when attention is trained or pharmacologically enhanced, long-range gamma coherence and theta-gamma coupling strengthen and feature-binding errors drop. Run double-blind trials comparing an attention training regimen versus active control, plus a separate arm with a safe, known attentional modulator. Measure coherence changes and binding performance. If attention boosts behavior without measurable changes in coupling, or if coupling rises without behavioral benefit, the link between timing and binding is weaker than we think. Population phase code readout. Prediction: Decoding stimulus identity and order from the phase of firing relative to local rhythms should outperform rate-only decoders in tasks with temporal structure. In humans with dense arrays or animals with neural pixels, train decoders on phase-augmented features. If phase adds nothing beyond firing rate across tasks designed for sequences, the phase channel isn't doing the heavy lifting we claim. Degeneracy and rerouting. Prediction. After targeted disruption of a pathway, distributed networks should quickly route around it with increased latency and reduce high-frequency precision, then regain precision with training that emphasizes rhythm. In non-human primates, transiently inactivate a mid-level node with safe methods, map delays and spectral changes, then train with paced tasks. If function returns without spectral sharpening or timing changes, rerouting may be purely structural, not interference-guided. Falsifiable fail states. Here's what would break the model. Single neuron or microcolumn deletions repeatedly, selectively, and permanently remove specific episodic memories without broader precision loss. Phase lock stimulation provides no advantage over random timing across multiple labs and tasks. Sleep TMR works irrespective of phase or strengthens uncued memories as much as cued ones. Precision of memory correlates only with local firing rates, never with spectral coherence or cross-frequency coupling. And a final stress test, predictive error weighting. Prediction, experimentally altering precision signals by manipulating neural models. If changing precision changes nothing about the projector's fidelity, then our UI plus interference story is overstated. Set the bar high. If we pass these tests, the projector isn't a metaphor, it's a mechanism. If we fail, we rewrite the model. Either way, the experiments tell us where you, the signal, actually sits. Identity in a distributed brain. Self as a dynamic reconstruction. If memories are patterns, then the you that keeps showing up every morning can't be a file either. The self is the most stable pattern the system can maintain under changing conditions. Body states, social demands, losses, wins, disasters. It's not a single location. It's a reassembled signal that holds shape because the projector keeps reconstructing it, moment after moment from overlapping codes. Listen to how it behaves. Wake up groggy, low energy, and the self you access is muted, cautious, slower. Hit a familiar routine, coffee mug, same playlist, same route, and your narrative sharpens. That's the system locking into a practiced attractor. The same hardware can render different selves depending on precision settings and cues. It isn't pretending. It's reconstructing the most coherent story available from current state plus priors. Narrative is glue here. Your brain doesn't archive a list of facts about you. It maintains a running model that explains your actions across time. When new events arrive, the model tries to fit them without ripping. If they don't fit, illness, grief, dramatic success, the model updates, sometimes painfully. People describe it as not feeling like myself until the projector finds a new stable completion that can include the shock. Therapy often works by supplying bridging stories, repeated in safe context, that the system can re-enter until they become the default reconstruction. Split brain findings make this concrete. When surgeons sever the corpus callosum to treat severe epilepsy, each hemisphere can operate with partial autonomy. Present a word to the right hemisphere through the left visual field, and the left hemisphere, the talker, doesn't see it. Yet the left hand, right hemisphere control can point to the correct object. Ask the speaking hemisphere why it pointed that way, and it invents a reason. That confabulation isn't a lie. It's the UI doing what it always does, completing a coherent self from partial data. 2 projectors, 1 body, negotiated interface. Zoom out to aging. As high-frequency precision drops and networks thin, the system leans on stable routines, rituals, familiar places, well-worn stories. That's not stubbornness, it's compensation. Shrink the hologram, boost contrast with cues. A chess player forgets new names, but still sees a board's deep structure. A pianist can't recall a neighbor's phone number, but can play the first movement by muscle and rhythm. The identity pattern persists by relying on frequency bands that still lock slow routines, strong themes. Ethics hides in this. Who are you after radical change? After brain injury, after neurodegenerative disease, after a personality-altering tumor? Law wants neat answers. Biology offers curves. Identity continuity sits in pattern stability and social reinforcement. Families who preserve familiar cues, photos in the same places, old songs, morning rituals, often watch fragments recombine into a personhood that, while altered, feels continuous. It's not sentimental. It's timing and context maintaining the attractor. Here's a micro story. A teacher with a left frontal stroke returns home blunt, less patient, not themselves. Over months, a routine emerges. Walking the dog at sunrise, reading aloud to a child at lunch, cooking a familiar soup on Thursdays. The old sense of humor flickers, then holds. The jokes are simpler, the timing different, but the pattern is there. The household acted like a scaffolding of reference beams, predictable rhythms that let the projector find its groove again. The dark read is unsettling. If the self is a reconstruction, isn't it flimsy? The clearer read is empowering. Reconstructions are tunable. Precision can be widened with breath and movement. Priors can be edited with experience and language. Cues can be curated. People who deliberately change contexts. New city, new.
Friends, new sleep. Know the awkward limbo when no attractor holds. Then a routine sticks. A phrase becomes catchphrase. The new self stabilizes. The projector learned a different completion. There's a frontier here in artificial restoration. Brain, computer interfaces that decode intended movements, let paralyzed people type by imagining handwriting. The decoded pattern isn't a handwriting file. It's a dynamic motor program reconstructed from population activity. As decoders improve and the user trains, the system's mutual prediction tightens. Identity expands to include a cursor or robotic arm without metaphysical drama. The projector's model of me grows new effectors and integrates them as long as timing is reliable. What about moral responsibility? If the self is a pattern that can drift, our choice is yours. Responsibility lives where patterns are stable enough to predict and alter. When disease desynchronizes networks, control narrows, we adjust expectations. When training tightens timing and expands options, control widens. We expect more. This isn't a loophole. It's a humane mapping of agency to the bandwidth and precision the projector can muster. From another angle, the self is a social hologram. Other people act as reference beams that help reconstruct you. They reflect your phrases back, amplify certain traits, starve others. Couples share jokes that don't land elsewhere. Teams adopt rhythms that make them click, remove the social beam. Loneliness, isolation, and the reconstruction loses contrast. Reintroduce community with predictable rituals and the person brightens. That's not metaphor. Those interactions tune neuromodulators, rhythms, and priors. There's a gentle warning embedded. The feeds you consume, the rooms you sit in, the people you let set your tempo become the angles of your reference beams. They change which attractor wins when the system idles. If you want a different self, don't white-knuckle traits. Change the timing, the cues, the audience, and the story will shift. So where are you actually located? Not in one spot. You're in the pattern that your body and world can most easily reconstruct again and again across time. You're streamed, not stored. And that means continuity is a practice. Practical, upside. Learning, therapy, and daily upgrades. If the projector is tunable, then daily life is full of knobs. Start with learning. Don't just reread. Build space cues that line up phases. Study a concept, then ping it later with a tiny handle, a keyword, a sketch, a sound, right before sleep. The small cue acts like a reference beam. Overnight replay stitches detail. Add multi-sensory encoding. Pair text with a quick doodle, a whispered summary, a finger tap pattern. Each channel carries overlapping frequency content, raising the odds that one fragment will complete the whole tomorrow. Timing matters more than time spent. Use short, focused bouts bracketed by 1 minute of rhythmic breath. 4 seconds in, 6 out. That downshifts arousal and widens temporal windows in which spikes bind. Then teach your brain when to expect retrieval. At the end of a session, preview 3 likely questions out loud. You're planting phase-locked addresses for your future self to call. Hours later, walk for 2 minutes while mentally recalling the answers on each step. Movement provides a metronome. Steps become their own reference beam. For memory-intensive work, try light entrainment carefully. Soft visual flicker or auditory beats at comfortable rates can nudge attention and phase. Keep it modest, a gentle 40 Hz texture for a few minutes at the start of encoding. And test whether it helps you, because responses vary. The principle is the point. You're not forcing neurons, you're offering a timing scaffold, so interference patterns settle cleaner. Therapy turns the same knobs with higher stakes. For trauma, begin with context, safety, and precision, tuning before touching content. Breath pacing, weight through the feet, slow tracking of the room. These reset baseline rhythms. Then approach fragments. Smell, tone, posture, inside a bilateral rhythm.
tapping left-right, slow saccades, alternating tones. You're lowering gain and controlling timing while retagging the cue. Later, pair the reclaimed cue with sleep. A short replay of the new association before bed invites consolidation. Track progress by how quickly and how fully the old pattern completes. As high-frequency snap fades, the flashbacks dull, the cue becomes ordinary. For anxiety, widen bandwidth. Start the day with a fixed ritual that finishes a bit faster than your default. A brisk walk with a count to 5 on each exhale. You're giving your system a predictable metronome and a small success. Then practice precision shifts. Notice a worry image, label it prior. Look for a single sensory mismatch right now. Temperature on your wrist, weight in your shoes, and say softly, updating. That word anchors a micro-behavior. Tilt attention to error.
Signals, so priors can loosen without a fight. For depression, restore sleep architecture and boost contrast. Protect morning light. 10 minutes outside within an hour of waking retunes circadian phase and nudges neurotransmitters that shape precision weighting. Use low-friction winds to reintroduce phase coherence. A one-song tidy sprint, a single text to a friend at a set time daily, a pot of tea brewed the same way at dusk. Routines are reference beams. They let the projector find a path back to a self that acts. Cognition at work benefits from context chords. Before a complex task, play a 3-note sound or hum a bar you always pair with deep work. Sit in the same chair angle, place the mug on the same side, breathe the same 4-6 pattern. After a week, that chord will bring the state back faster. When you switch tasks, change the chord. You're multiplexing states so they don't bleed. Creativity loves cross-frequency coupling. Alternate novelty and consolidation. 20 minutes of divergent play. Free writing, sketching, instrument noodling, then 5 minutes of structure. Pick one idea and put it into a container, a title, a 2-line brief. The alternation is the point. Let fast rhythms explore, then let slower rhythms bind. Add brief context switches. Stand, look out a window, squeeze a ball on a beat, to reset timing between bouts. Many people feel ideas click on the return. Tools can be low-tech. A metronome, a breath app, a dim lamp on a timer, an eye mask for short daytime naps, a stretch band. The win is specificity. Decide which knob you're turning. Timing, cue strength, arousal, and match the tool. Entrainment isn't magic, it's scaffolding. If it helps, you'll feel tasks pick up smoothness and recall sharpen. If it doesn't, drop it. Safety caveat. If you live with epilepsy or migraines triggered by flicker, avoid visual entrainment and consult your clinician. If you're in active psychiatric distress, timing tools belong inside a treatment plan. Aging? Shrink the hologram, boost contrast. Keep the same parking spot at the store, the same hook for keys, the same opening line for names. Hi, I'm... Remind me of your name again? Layer cues. Pair names with a visual and a movement. Grace, as you trace a G in your pocket. Rehearse and sleep. A quick, calm run-through of new names before lights out. Family care can do a lot with little. Anchor meals to music from the person's youth. Place photos in spots where sunlight hits at the same time daily. Keep walking routes routine. The point isn't to trap, it's to give the projector stable angles so the person it knows how to render keeps showing up. In the end, daily upgrades are humble. Small beats, repeated cues, honest sleep, social reference beams, and light on the right rhythms. You're not hacking your brain. You're giving a biological hologram better conditions to reconstruct the life you want to remember. When the interface fails, and why that's hopeful. There are moments when the projector thins and you feel the scaffolding underneath. Anesthesia dropouts are one. You're in a bright room, voices clipped, a counting rhythm in your head, then the count is gone. No tunnel, no fade, just an edit. On the other side, you're the same story, but you missed a reel. That gap is what prediction looks like when it's paused. No model, no UI, nothing to report. It's eerie, but it's honest. Conscious experience requires the projector to be running. Migraine aura shows a slower failure. The visual field fractures, edges ripple, checkerboards crawl. Physiology tells us a spreading wave of changed excitability sweeps cortex. Subjectively, phase relationships slip. The interface tries to reconcile inconsistent frequencies and renders unstable icons. The lesson isn't cosmic, it's mechanical.
Timing matters, and when inhibition and excitation fall out of register, the world loses its crispness. Ego dissolution arrives through a different door. High-dose psychedelics, intense meditation, or extreme stress can loosen the coupling in networks that stabilize the narrative self. The boundaries that usually anchor "I am here looking at that" relax. The prediction that sensations belong to this body drops in precision. Some find this terrifying, others call it relief. Either way, you're seeing how much your sense of self depends on a tight, ongoing reconstruction. When the social and interoceptive reference beams dim, the attractor labeled "me" weakens, and the UI paints with broader strokes. There's a micro story that captures both the risk and the hope. A software engineer hits burnout and panic, heart racing, rooms tilting, thoughts looping. Medical workups come back dull. A therapist doesn't argue content, they target timing. Morning light within an hour of waking to anchor circadian phase. A 10-minute walk with a steady count. Brief, bilateral tapping while naming one neutral detail in the room, one body sensation, one breath count, twice daily. No philosophy. 2 weeks later, the dread still visits, but it doesn't flood. The projector has more bandwidth. Over months, the old loops lose snap. The world regains weight. Nothing mystical happened. Precision and phase shifted, meaning often hides in those recalibrations. When the UI fails, you find out which cues actually hold you together. A parent realizes that the 5 minutes of humming before bedtime aren't a sentimental add-on. They're the metronome that locks a child's world into predictability. An athlete learns that their pre-shot routine, the breath, the toe tap, the glance, stabilizes the projector under pressure. A caregiver sees that an old song isn't just nice, it reconstructs a person others had started treating as gone. The interface is fragile, but it's tunable. There's freedom in admitting it's an interface. If perception is a UI, you can stop chasing perfect accuracy and start building useful icons. You can curate inputs that nudge identity in directions you choose. You can design rituals that make difficult selves easier to load. Grieving selves, focus selves, brave selves. And then you can unload them when they're no longer needed. You're not faking, you're selecting attractors. The darker thought, death, enters differently when you accept streaming over storage. If the projector stops, the show ends. That's blunt. But it also places value on the patterns you reinforce while you have the beam. What you practice becomes easier to reconstruct. Kindness practice becomes reflex. Curiosity practice becomes default. Skills practice become parts of you that others can help call back when your own system is thin. Families and communities act like external plates holding shards of your pattern. Stories, phrases, gestures that can be relit. That doesn't answer any metaphysical question. It lands a practical one. Choose the patterns you want echoed. And here's the hopeful core. Failure modes are windows. Auras, dropouts, floaty dissociation. They aren't just symptoms, they're diagnostics of a system that can be tuned. Precision can be widened or narrowed. Phase can be reset. Priors can be revised. The UI can get crisper with the same hardware by changing timing, context, and practice. When the building feels less there, it's not because reality left. It's because your projector needs calibration. The knobs are small. Breath, beats, light, sleep, people. But they move a big machine. Resolution and broader meaning. Your brain isn't a hard drive. It's a projector that streams a world and a self from timing, rhythm, and overlapping patterns. If you want a sharper life, train the beam. Subscribe for grounded deep dives and watch the next episode on memory cue engineering. Simple protocols that measurably boost recall. Share this with someone who remembers it perfectly. Let's test that together and compare notes. Appendix, source integrity and boundaries.
Let's set the guardrails. We've told a story, but the story stands only where evidence holds. Here's what we're claiming, what's plausible, and what we're not saying. So you can check the beam, not just trust it. What's confirmed? Distributed encoding isn't a vibe. It's a century of convergence. Lashley's lesion data showed mass action and equipotentiality at the behavioral level. Modern work tightens it. Lesion volume often predicts degradation better than location for complex tasks outside of known bottlenecks. Oscillatory binding is measurable. Local field potentials reveal gamma for feature binding, theta for sequencing, and cross-frequency coupling that relates to memory performance. Sleep replay is robust. Slow oscillations grouping spindles and ripples with targeted memory reactivation improving recall when cues align with slow wave upstates.
Plasticity and degeneracy are table stakes. Function reroutes after injury. Perilesional recruitment and contralateral support show up in imaging and in clinic. None of this is controversial. What's plausible? Frequency domain processing as a core organizing principle fits receptive field math and known physiology. Gabor-like filters capture cortical tuning and vision. Phase of firing codes add information beyond rate in several systems. The hologram here means distributed spectral codes plus interference, like summation in neural populations. Pattern completion and separation are well supported in hippocampus and cortex. It's plausible that phase and frequency act as addresses to multiplex overlapping content, and that timing interventions sharpen recall by improving phase alignment. These are active research areas with promising, but not universal replication. What's speculative? Quantum roles beyond chemistry are not in our claims. Warm, wet tissue decoheres fast. You don't need long-lived quantum states to get interference in classical fields. References to holography are about signal processing analogies. Fourier spaces, interference, multiplexing. Not the ADIS CFT holographic principle, not non-local consciousness, not spooky action coordinating memories. When we nod to quantum-inspired math, we mean shared formalisms. Wigner distributions, Hilbert spaces as analytical tools, not physics mechanisms living in dendrites. Where researchers propose quantum tunneling in ion channels or microtubule coherence, those are hypotheses with mixed evidence and heated debate. They're outside the scope of claims we rely on. Boundaries of the model. The projector metaphor explains a lot about robust recall, graceful degradation, and cue-driven completion. It doesn't replace synapses, molecules, or development. Synaptic plasticity is the substrate that builds and updates the patterns. Glia, neuromodulators, and vascular dynamics shape gain and timing. Developmental constraints, genes, and experience define the space of patterns that can exist. Our model also doesn't say everything is frequency. Place codes, rate codes, and population trajectories all contribute and can be dominant in specific circuits. Source integrity. We drew on peer-reviewed neuroscience and mainstream physiology, lesion and stimulation studies, hippocampal ensemble recordings, sleep and TMR work, visual cortex receptive fields, phase coding papers, and clinical rehab literature. Historical vignettes, Lashley's maze work, awake craniotomy stimulation, split brain, are well documented in primary sources and reputable summaries. We avoid lifting numbers or quotes without clear attribution. When exact wording mattered, we used quotations with context. Where the literature conflicts, we flagged it as contested and avoided settling debates with anecdotes. What would change our mind? Clean, repeated demonstrations that precise microlesions delete single episodic memories without broader precision loss. Phase lock stimulation failing to beat random timing across tasks and labs. TMR effects that ignore phase or strengthen uncued items as much as cued ones. Decoders gaining nothing from phase of firing beyond rate in temporal sequence tasks. Strong correlations between memory precision and local firing rates with no relationship to spectral coherence or cross-frequency coupling. Any of these would force a revision down towards simpler localist accounts. Ethics and hype. We don't sell cures. Rhythmic tools, breath pacing, and cue engineering are supports, not substitutes for medical care. Visual flicker can trigger seizures or migraines. Anyone at risk should avoid it and consult clinicians. Timing interventions belong inside evidence-based plans for PTSD, anxiety, depression, or cognitive impairment. We reject telepathy claims, remote healing by holograms, and manifestation frequencies. Credibility matters. The good science here doesn't need glitter. Invitations. Try the practical tests, space cues before sleep, add a gentle metronome to study, use bilateral rhythm when recalling hard memories in safe contexts, track whether recall Sharpens. Share results. What worked, what didn't. If you're a researcher, push the falsifiers. If you're a skeptic, keep us honest. Bottom line, you're not stored, you're streamed. Optimize your signal with timing, cues, sleep, and people, and keep demanding evidence for every knob you turn.